So up next we have Patricia Hunt from Victoria University of Wellington and SNAP, a network. She'll be speaking on a network hub for simulation, numerical methods, analytics and programming. Welcome, Patricia.
Thank you for the organisers for the invitation to come to this meeting. I find it really fascinating, and it's been great making connections and networking with people. So I'm an academic, and we've built this hub at Victoria around simulation, numerical methods, analytics and programming, and I'll tell you a bit more detail about what that is. But who am I? So I'm a professor of theoretical and computational chemistry. I came in from Imperial College in the UK in London. So that means I use quantum chemistry, the Schrödinger equation, to work out where electrons and nuclei want to be in molecules and during reactions. And so the theoretical bit means we look at sort of physical processes and make correlations and relationships. We write mathematics for that, and then we turn that into codes, which we then run to simulate where the electrons are. And so we do a little bit of that, but the field is very, very wide. And so the other part of what we do is computational work, which is really simulating using other people's codes and programs at different levels, from classical through to quantum, again, where the electrons and nuclei want to go. And I just had a couple of... So this is just a little animation. Each structure there is a different thing that we've calculated on the HPC. And then we work out which is the kind of the lowest energy one, and then we put it together with other molecules to look at a reaction, and we look at transition states, and what we want is a transition state with the lowest energy. And so we're helping our our experimental colleagues identify good structures to build and make in their labs. And what we do in that process is we work out some energy, so that's the red box there. We worked out which was the best combination for this, so we got minus 70 kilojoules per mole versus minus 40. And we do a lot of analysis of the electronic structure itself, so topologies, looking at surfaces and potentials, and so I've got a few graphics up there to spice things up. And a lot of the graphics are numbers, aren't they, under the hood? There's a lot high density of numbers, and we interpret them. So what is VUW-SNAP? So simulation, numerical methods, analytics, and programming. And the purpose of this hub was for our academics and support staff to get together, bring computational researchers who wouldn't normally talk to each other together to talk to each other. We wanted to improve the numerical skills of our graduates, our PGs and our postdocs, because there's a bit of an education gap at the moment, and a lot of them come into our disciplines without these skills. And we want to promote what we can do externally as well. A lot of us are not that gregarious, and engaging and getting these contacts with industry can be a challenging task, and so it's to help people along that line and to help our graduates into their next job, so trying to connect with industry a bit more. So this is the beginning. So the real beginning is I came over and I had a look at VUW, and one of the exciting things that I liked about it was the open access to the HPC. I didn't have to pay for it, the support was there, and when I went and met the support staff, boy, were they amazing. So they really wanted to connect and be engaged and support my research. And then once I was in Wellington, COVID, I left most of my group in the UK. I was starting to build from scratch. And the groups here are smaller than tend to be in Europe, and I found that we can lose skills because we have these smaller groups and we don't have these sort of code gurus in the group who help people along their path. I found students coming in with quite low math skills, which also meant quite low computational skills. Didn't know what a Unix or a Linux interface was, no scripting, no coding. And so I was sitting there complaining at lunchtime one day, as you do, to burn off steam. And other people were going, yeah, I have that problem too. I have that problem too. I was sitting with the physicists at this point. And so we decided all to get together. We had a few coffees in the cafeteria and decided actually we would do something about it. It was us who was going to build this thing. And what we did is we sent out an email to our people we knew or people that I'd just met sent out emails to people they knew. And what was amazing was it grew. So it started out just the science faculty, but suddenly I was getting requests from other faculties, other people, can I be involved? What's going on here? We have this problem too. And so we started to pull things together, and one of the first things we had to do was decide who is SNAP going to be for. And we decided that it's going to be for physical or other scientists who are not computer scientists, who are not native coders. That's not their research job. It's for people who, like me, are a chemist, have chemical training, and then pull codes and computational in and use it. So we don't have that deep training that other people have who have come through the comp sci. So I've just mentioned Yvette here, who does galaxy cluster models, and Stephen, who does large language models. So it's for anyone who does numerical manipulations, modelling, simulation, coding, scripting, processing data with a computer. And we found we had a wide range of people come in, so natural sciences, social sciences, linguistics, health, engineering. So it really started to grow. So what I am saying is it's not people who specialise in AI or neural networks or deep learning. We're going to pull those skills in as we need them, but that's not our base research program. And it's for postgrad academics because we don't want to impinge on the university money-making areas of having undergraduates. And also I'll talk a little bit later why that's not really a suitable space for our graduates to go and learn the skills we need them to know. So we had academics who had coming through, they'd been physical scientists or social scientists, and they kind of ignored the digital aspects, but now they're realising they really need to get engaged. They really need to start understanding this field. And they're not the natural people to move into this field, so we wanted to support them. Or we're people a bit like me who use quite complex packages, have a ad hoc learning, learn a lot on our own, do lots of stuff, and we need very special technical-based knowledge in that particular area. We're not so interested in doing that thing over there. So it needs to be things that for time-limited people, quick learners, and very targeted skills. And then there's this problem with our postgrads not being trained because they're not coming from a comp sci, they're coming from a chemistry undergraduate degree or a bio undergraduate degree or a linguistics undergraduate degree. And they're not very motivated to do a whole term course. They don't want to pay for it either. And what they need is something that's very on demand because they're motivated, I need to do this for my project. And that's when they start getting engaged. And we need to be able to deliver these skills when they're engaged, and we need to be able to deliver them in a short time span and sort of, well, I called it learn on the fly. The other thing that I found as an individual is that, and the other people, of course, in the group as well, is that the field's exploding. And it's really hard to keep up as a busy academic. The scale of resources has changed. So although I'm on the HPC, quite a few people were doing desktop and they want to move into the HPC and cloud. The number of programs, algorithms, codes, depositories, resources that you can now access, how do we make our pathways through those? And so it was about trying to upskill people, and in doing so to improve the research outputs, to make us more effective, more efficient, and do more research, make us more internationally competitive. And so what we did is we set up a brainstorming meeting. We had a great turnout, more than 50 people. I was expecting 15. And a wide range of faculties, and we did some work with, we broke into focus groups. So we had a facilitator with each focus group. We used Padlet, which you've seen a little bit of already. And during it, we also gave a Qualtrics online questionnaire, which we did in the workshop so that we got a very high response rate. And boy, did we get a lot of data. Here's a few quotes of what people were talking about. So most of our staff using these technologies are self-taught. While there are a few who had while few have formal training, like a peer group to learn from, keep abreast of new developments or discuss the problems they encounter. So these silos are all around and they're enclosed in their own discipline. What we want to do is join these people up so that they can talk to each other. I don't have time to go through all the quotes, but hopefully you've had a bit of time to read one or two more. And when we got it all together, we kind of came up with 3 categories that people wanted, because we asked them, what do you want? And they fell into together, training, and translation. So together was building the community, sharing expertise, finding an expert who can help you when you get stuck, sharing knowledge about resources and how to use them, getting people on to Rapoi or onto Nessie. Find out about better software, so showcasing software to each other. Training, we talked a little bit about providing these resources, and stop repetition. Each individual section was giving the same beginner's Python course. Much better if they can all go to a centralised system and learn together in that environment. And I talked a little bit about translation, their difficulty in engaging, and so we wanted to try and make a more visible platform and try and engage sort of industry internships and things like that, have a resource where we can go out and look for these as a group, because then we have more sort of punch. And so we formed the SNAP working group, and I'm going to start with the eResearch staff who helped us do this, because they're really important. It's sort of together. You talk about co-design, co-creation, and so these are people probably familiar to you. So Johnny was very supportive right at the beginning, let people in his team get engaged with us and spend time with us, our HPC guru, who we've just lost. And technology-mediated learning, our IT systems, and Matt sitting over there, our network guru, as it were, so helped us connect up with lots of different spaces in the university. And then we've got sort of the academic side of things, so I do a lot of motivation, keep people working hard, and then I have had 2 co-Is who do a lot of the grunt work for me, younger staff, which I can help mentor up through, and they can gain experience in this kind of thing. And then we had champions in each faculty that individual people in that faculty could go to if they wanted. And really, we've been doing this very light touch, so we have a Zoom meeting every month. The meetings are amazing. They're packed with ideas and things we want to do, and I come out of them very energized. And I'm amazed at the time academics are willing to take out of their research, out of their admin, out of their teaching to contribute to this kind of thing. So what have we done? Remember, all contributions are voluntary. We created a logo. Here it is. We made a website. We put some stuff on it. We've got blogs and things going. Still lots to do there. We started a regular coffee meet. So there's a photo there from one of our meetings. Sort of 20, 25 people would turn up. And we had some local group lunches. We run short seminars. So there's one we ran recently. How can ChatGPT help your research? So we have people from the group to come and give 10-minute talks from around the university, and we can discuss sort of in an open environment. That one was massively oversubscribed. We had people standing in the back. We run specialist workshops, so in an area for a particular code. I think I've got one up there from Wellington who does molecular modelling docking, and one from Stephen on his large language integration. We also want to not repeat stuff, so we want to direct users to central resources. So until recently, we had great eResearch support for, say, developing or understanding the beginnings of Python or GitHub or things like that, and directing people outwards to good resources, because one of our problems is people picking up things from the internet and building and getting bad habits or using strange things. We advertise our link and contribute to specialist meetings. So there's a few there: Antarctic Science Winter School, Fluids in New Zealand, Capital City Complex Systems Symposium. So we sort of engage at that level. We have a few tutorial and online guides that's still developing, and we have our largest SNAP meetings. And we bring researchers together and we tell them, you're not there to talk about your research, you'll talk about the codes you use, how you use them, and talk to people about what's great about them or what's bad about them. And that's been really well received, because it's the spreading of knowledge of, is there a code that can do what my current code does better? So here's my evolution of SNAP. So our lunchtime discussion and contacts, workshops, SNAP. We actually managed to write our fully costed internal business case, and we got 100K. And then I guess many of you will know that Victoria University has been under substantial financial problems, and so this became retrenched. We've had an issue with sort of low morale, a bit of a lower turnout. And we've had our e-support staff slashed, and we've had our academic staff slashed. I think we've sort of hit a low, and now we're ready to go on the way back up again. Things are stabilising, we know what we're working with, and our core is still there. We're there, we've got ideas, we've got a meeting next week to plan out for the next year, and we've got lots of ideas of what to do. What we're going to have to do is, I think, slow down a little bit, because we might do a bit of burnout if we rely on fewer staff for fewer things. What was an unexpected return that came out of this was the importance of having a cohesive voice upwards into senior management. So we were able to engage with heads of school, deans, deputy vice chancellors, and say that HPC is a very important part of Victoria's life blood, as it were, for researchers. We need it. We had a central unit to collect and condense information. When I was collecting information about how many grants for our sort of letter to support the eResearch staff, I could collect lots of information from different people. And we're supporting each other in difficult times. We're supporting the eResearch staff, and the eResearch staff are supporting us as best they can during this very difficult time. So I think we've come out as a stronger community out of this, but also a recognition we need to engage as a group upwards into the more senior management to show them that we are really important. So the positives, we're still here. We have a strong core of champions. We've created a collective environment. We're on an upwards trend, and it's pushed for us to engage more nationally. What's on the future? A smaller number of activities, but I want to bring in more PhD and postdoc engagement. They have a bit more time. We can use that resource. We haven't really done it yet. Engage more nationally, try and leverage resources where we can, and sort of try and participate in strategic decision making now, looking for the future of the resources that we want. And I'd just like to say that you want to ring fence money perhaps, but our PhDs and postdocs, if they come out from us better trained, that means they go into your research group in another university, and they're more productive from that point onwards. So there is a reason to be collaborative and share in this environment. So I'd like to acknowledge my co-leads, Brendan and Yvette, who do lots of hard work, the strong input from Matt, who's dedicated lots of hours as well as helping us connect up, all the champions in the working group who make the contacts sort of locally and make the activities that we do on the ground. And I'd like to thank you for listening.
That was fabulous. Thanks, Patricia. Does anyone have any questions that they'd like to share? We've got about a minute to... Yep.
One over there.
Is there one most obvious thing, external help you have in mind that could be used in the near future?
Absolutely. Well, we've lost our people who are going to teach our students the low-level skills, get them into Python, get them into GitHub, so the ResBaz and the online community where you can sort of learn that way, I think is going to be one of the things that I've learned more about at this meeting, and I'm really going to try and target sort of at the meeting next week, is can we engage with that a lot more.
Okay, up next we've got Daniel Bentall from Plant and Food Research, who will be speaking about project orchestration and building self-service tools. Welcome, Daniel.
Tēnā koutou katoa, ko Daniel Bentall tōku inga. I'm here to talk about project orchestration and self-service tools. And to kind of set the scene, I guess, I'm going to first talk a little bit about machine learning model development, since that's what I do a bit of. And the way I see it, it's kind of a process with a few cycles in it, kind of a data-centric or focused cycle on the left in the diagram, iterating on the data itself and data processing and labeling the data. In a more modeling-focused cycle on the right, you're looking at the parameters to the pipeline or completely different pipelines or different approaches you might take. And some sort of exploratory data analysis where you want to see what the, maybe what some of the stats on your data are or on the labels, or how's the model performing over different groups of the data, this sort of thing. And from there, you're often making decisions about what's the next step. Is it get more data, label more data, run the modelling or adjust the modelling, or eventually deploy the model to some kind of use. And it's sort of characterised, I guess, by a mixture of manual and scripted tasks, and quite an evolving sort of set of pipelines and data and labels and sometimes even the objectives that you're aiming for. You realise you actually have to tackle the problem a different way. So I kind of thought maybe it's good to see what the evolution of a project might look like. And for me, I do a lot of computer vision work, and if I'm looking at some cutting edge model, I'd probably start with looking online, Hugging Face, GitHub, looking for sort of training scripts and models and that sort of thing. And so the first step is like just get that running. So pull that down, build a Python virtual environment or something similar, which can be a lot more hassle than it should be. And then, train a model. And you could start playing with modelling at that point, but probably not much point because you're just working with the sort of the example data that it comes with. So next up, you obviously want to run that stuff on your own data. And, well, plant and food, often that's, photos of plants or fish or insects or microscope slides or all sorts of stuff. So you've got your data set, or the scientist has provided you with one, and now you need some way to ingest that data potentially. Then you need to do some labeling with it. So now we use a labeling tool, a web-based labeling tool. So we need to get the data to the labeling tool, do the labeling, get the labels back out again to run some training on it. And then usually they're not in quite the right shape for the training pipeline, so you need to do some sort of pre-processing pipeline. So you've got these different pieces. You can at this point you can start doing a bit more fiddling around with the training or the labeling, but it's definitely a good idea to add some evaluation in. So a very simple evaluation here of just splitting the data and doing a train and a test separately, and then use that kind of the metrics from that instead of just the very simple metrics from before, I guess. And now, it's getting a little bit more complex. There's a few more pieces. Still not too complicated, I guess, overall, but you've got a few moving parts. Next up, you might start to group these things together. So you've got like maybe a pre-labeling pipeline, and it's got a few more pieces to it. You've automated the interface to the labeling tool, so you're sending data through the API and pulling it back down through the API in the modelling phase. And these pieces, you're kind of starting to build little mini pipelines within your kind of project flow now, and maybe you want to deploy your model as well. So there's another pipeline there. It's probably good to note as well that all of these pieces are in flux as you go through the process. So not just the data, but the pipelines, the parameters, swapping out pipelines, trying different things, all sorts of evolution there as well. And then maybe you want to go somewhere more advanced. You might want to do some kind of active learning, and maybe you want to use a foundation model. So now you're starting with a model before you've even labelled any data, and the model can have a crack at labelling your data for you. Maybe you have a method where you choose some difficult examples, some images that the model found difficult, and some other images as well. Well, it doesn't have to be images, it's just what I'm used to. This applies to all sorts of data. And then, do some label refinement in the labeling tool, fix up where the model isn't quite got it right, and kind of repeat until you've got something quite useful. So there's lots of different pieces here and slightly different shapes to these things. And I found the orchestration of all this, I guess, that's what I'm kind of defining as project orchestration. So managing the data sources, the pipelines, and the artifacts that you're generating. The whole thing is quite iterative and evolving, and you need to manage that. You want to be able to handle arbitrary workflows of pipelines, and you want to be able to it makes it a lot simpler, I guess, if you can think of multiple levels of pipelines as well. And you want to this concept of lineage for data or for the whole project, and I'm sort of saying spatial lineage of like how data is moving through your pipelines. This piece of this output, where has it come from? What pipelines has it gone through, and what was its sort of input data? And then sort of temporal lineage of the whole project evolving and all of that. So how do you handle all of that complexity and all of those details? And also a lot of projects I've found you're kind of dealing with different, quite diverse tasks that you're wanting to bring together sometimes. So you might have different tools that you're trying to use. How do you bring those together within a project? So first major component is data versioning, which hopefully, versioning in general, I suppose, actually, which, Git, I'm sure plenty of people are hopefully quite familiar with that, but it does struggle with data. And so data version control is a reasonably simple open source tool to tackle that problem. Basically, the data is stored separately and references to the data are versioned in Git. And it's a pretty simple concept, but it works very well. And so you can now version your input and, if you want, intermediate and output data as well, and have that backed up in the DVC remote. And you'll be able to, move backwards and forwards in time, change versions, change branches, all the normal things that you can do with Git, but now with data as well. And you also want to be able to version the pipeline definitions. They're kind of code, and you could do that just with Git, but DVC has a nice, simple feature around that as well. So now you've got your spatial lineage, you've got that sort of directed graph of project steps, which I'm calling actions, and the temporal lineage from the Git history. So another major component is the pipelines that you're building your project out of. So I'm seeing kind of multiple levels of pipeline as quite a helpful concept to have. So if there's the project level, you've got the different actions there, which are usually manually triggered. But this is like, so the pre-labeling action I mentioned before, that's going to do a whole bunch of steps inside that and set you up ready for labeling. It's basically only delineated by where the manual step is that follows it. And so you've got these actions. The actions then composed of, they can be a DAG, a directed acyclic graph, basically just a list of steps with connections between them, of stages is the terminology DVC uses, and so I'm adopting it. And then the stage is basically, it can be anything really, it can just be arbitrary code or shell command, but what I like is using another DAG of prefect flows, and I'll get on to what that's all about. So prefect is a workflow orchestration tool, which basically means you can write pipelines in it. It's Python-based, and that is very convenient for a lot of data manipulation stuff. And you can basically, so you can develop these flows or pipelines in these separate flow libraries. I'm going to get into that on the next slide, really. So then you can also have project templates. So this is like, you've got a list of actions. That might be a standard sort of list of actions that you would have for an instance segmentation project. So you can build a template for that, and then you can build a template for whatever other tasks you do. So the flow libraries, basically a Git repository for a specific kind of software environment, so PyTorch or whatever. And we've got, within that, that's where we might build all of the kind of standard libraries that we use a lot in whatever task we're facing. And they can be, you can have a number of these libraries. They're completely independent from each other and from the projects. They're basically just like a set of reusable pipelines, which generally useful. And if we define these as prefect flows, they can be sort of modular and composable. It gives us some benefits. We can deploy these to a server, a prefect server, and then now it decouples the pipelines from the environment that they're getting called from. So now you got the pipelines here, and you got the project over here. There's actually no direct dependency. There's an indirect dependency there of the project will use these pipelines. And then any kind of project-specific information is going to be parameters to the pipeline. So the pipelines are generic enough for that. And so currently we've got some flow library repositories that we're developing, just fairly standard stuff, general data manipulation things. Supervisor is our image labeling tool that we use, so the API for pushing and pulling data to the labeling tool, and then one for PyTorch and Hugging Face, where all the deep learning code is going to exist. So another view of this kind of platform sort of thing. We've got a CLI. It's called DPFRI. It's pronounced DeepFry. It's short for Deep PFR Intelligence. Yep, it's the command line interface, which would be the sort of first, I guess, way to interact with a project. Just simple. You can create new projects. You can run actions that the project has. And then there's the project repository itself. Can be a very minimal thing, I guess. It's basically just tracking the data and the pipelines of the project, or the actions. And then the flow library repositories, where all the heavy lifting is done, or all the complex code, I guess. That's where you've got a bunch of those off to the side there. They can define the code, the software environments required, the hardware environments required by the code. So the actual kind of workflow there is the user runs the action in the command line interface. That triggers off some things. So the command line interface reads the action definition from the project and starts a flow run to act on that, assuming that the action has a flow run. Could just be arbitrary code, but generally speaking, for the purpose of this, it's triggering the flow run, so it's sending a message to the server to say, I want to run this pipeline with these inputs or parameters. And then the prefect system basically will spin up the workers as needed. It can submit to Slurm, can start up containers, whatever. You can have workers in different places, and it'll run. Oh, I better speed up. All right, it'll run things where they need to be with the software they need. And then the flow will write the output to the project, and then the CLI is going to version that. So do all the Git and DVC actions required to get all of that stuff versioned. So self-service tools, basically, I think, if you've got a lot of similarities between projects, or if you have stages that don't actually need much domain knowledge to run them, they might need a bit of domain knowledge to build those pipelines, but they may not need much to run them. And it's a good time to get into some self-service tools. So computer vision, often the case, it's almost formulaic, at least to get started. Images, labels, some pipelines, and you can create a computer vision model. And another one is if you've got recurring data processing needs, then it doesn't have to be the developer who's running those pipelines all the time. It can be the users of those pipelines. So this is a 3D reconstruction of an apple tree in Hawke's Bay. There's a whole lot of steps that need to happen. You can see a bunch of cameras in this view here, those little red triangles. These steps can be, each of them, different pipelines, that can be all sort of automated, and a user can run it. So they've done another scan, they want the new outputs, they can just run that themselves. They don't need the help of someone very technical to get it to work. So yeah, I kind of see the self-service tools as, you know, project orchestration plus the pipeline libraries and the template projects. You've got a self-service tool, and you can any kind of automatable step can be sort of built into these actions and form, you know, aid that tool. One line setup of a new project, and you'll get something like that diagram in your project ready to go for your new task. And one line execution of any of those actions, you know, deep fry run the modelling stage and it will run that for you. So very simple for users. And all the versioning stuff can just be handled in the background in a fairly naive way, but it does the job. And, you know, integrate it with different tools, like the labelling tool, for example. And you can get a bit more control with configuration files. Yeah, so, well, I wasn't probably even going to do a demo, but I thought it would be great, you know, months ago when I signed up for this to do a demo, but I spent too long on the diagrams, so instead I just run through it like this, create a new project, run the pre-labeling stage, do some labeling in the app, run the training stage, take a look in your, whatever the EDA tool might be, maybe it's just a report, whatever, and then deploy the model once you're happy with it, or repeat those other cycles if you're not. So, yeah, there's a lot of things that that will take this a lot further, I think. It's, you know, it's good to have these separation of concerns, I guess, but what makes it easy to develop these reusable pipelines is having some standardization of data and formats and for the common tasks that you're tackling, because then it's really a lot easier to build out a lot of things more quickly. Integrating with other tools beyond just the labelling tool. There's lots of great tools out there which don't need to be reinvented. So good to work with those where it makes sense. And so maybe that graph of all those actions, manual and automated, you know, they can be, automate the generation of that. That can be a great piece of documentation for the project, for onboarding, whatever. Also, maybe it can even be sort of a control center there. You can, you know, click on the labeling or the pre-labeling, and it will, you know, and then get it to run. You don't even need a command line interface. Open sourcing is something that I've been thinking about and tossing up. It's kind of like, surely a lot of this stuff is relevant to many, or maybe many people have lots of good ideas which I should have thought of already, you know. Could be a really interesting thing to try, especially in the kind of local environment. So yeah, in summary, got a sort of a lightweight project orchestration layer or framework or tool or platform or something. It can, you know, it really doesn't have to add much to a project. Sort of, if you've got a Git repository already, it's not adding any dependencies in there. You just need this kind of separate tool, the command line interface, and you can just start working through this concept. You get the lineage, get a nice clear definition of the project. I've always come back to old projects and I'm like, where do I start? There's all this code and pipelines. I'm like, you know, what was running first? And yeah, you know, this is trying to solve that kind of pain. You can, yeah, decouple the pipeline code. So I've got, you know, lots of different libraries. They've all got their own code bases. You can use them all from this project or from any project just by, you know, using this kind of prefect deployed flow sort of concept. And yeah, should be, in theory, very easy to build self-service tools. Pretty basic ones, but pretty functional, I think. So yeah, maybe I see it as kind of an emerging framework. There's lots of gaps, but it's just new. So I think it's got some potential. Yeah, and thanks to all these people from Plant and Food who have contributed. Yeah, a lot of thanks to be had, really. Thanks, Chris. Thanks, and Harris. Yeah, great. Mihi nui, thanks.
Next up, we've got Alexander Pletzer from NIWA. He's going to take us fishing for parallelisation. I'm sorry if I am completely butchering this, for parallelisation strategies.
My name is Alexander. I'm working for NESI. I'm located NIWA, so which is in Wellington nearby. Thanks for organizing this session. I really appreciated all the talks. Great to hear about Patricia and you know, the sort of setting up that collaboration, upskilling researchers and so forth. Great to hear also about you know, workflows. These are all activities that we tend to be involved in. This is essentially about a consultancy that we had, which was a little special because most of the time we work with researchers here in New Zealand, but in this particular case, the researcher was located physically in New Caledonia and was working with fisheries, modeling fishing, modeling scenarios. And her name was Ina Senina from the Pacific community. Also worked with Chris Scott, who unfortunately was not able to attend this conference because he's running some sort of kayak trip or race or something really important. But anyway, the context is simulating the density of various tuna fish species in the Pacific, and you see some examples here at the top. You know, the red color presumably represents a high density of tuna fish. The idea is that once we know how many tuna fish there are in the Pacific and their reproduction cycle, you might be able to harvest them in a sustainable way. So this the application would be in terms of fish stock management mostly. The code, so we tend to be exposed with different codes. You know, in this particular case, it's a C++, written in the C++ programming language, currently running serially, and it solves what are called the advection diffusion reaction equations. These are just you know, spatial equations with a time dependency sort of evolution, a little bit like the Schrödinger equation in some sense. And the an important part of that research is that there are some parameters, like in many applications, we don't really know what those numbers are. In this particular instance, we get those. We try to infer these parameters from observation. So you have trawling boats across the Pacific. They catch a number of tuna fish, and this tends to constrain the system of equation in one way or another. So, but the problem number one was that code, CPODIM, was actually taking days to run, which makes it a little bit unwieldy when it comes to making decisions in terms of different scenarios. So the carry-on message, because I know that this is the last talk before lunch, so some people may fall asleep, but that there are many ways, you know, you can accelerate a code. And when we work with a scientist, then we sort of look at all these possibilities. We sit down and then we consult with them, and they drive essentially. They're in the sitting sort of on the driving seat essentially of the project. All we're doing is just laying out, you know, all the different options. We can see, you know, GPU threads, MPI, vectorization, workflows, and so which one should we use, right? I mean, that's the big question. And so the advantages and disadvantages, but here are just three of these options that we considered more seriously. You know, vectorization, shared memory, distributed computing, that means basically MPI. And each of them, without going into the details, I mean, each of them has advantages and disadvantages. And sometimes it's just a little bit of effort, but then the reward is small. And sometimes it's more effort and there is more reward. That's something to keep in mind. We understand that everything that is labor intensive, you know, you have to balance essentially the investment in terms of time with against the benefit that you're extracting. So the vectorization, what is it? Well, the first thing that you have to do is you have to profile the code, and then hopefully you're going to find a loop somewhere, and it says maybe 80% of the time is spent on this particular loop. If that's the case, then then that's great. In our case, I think it was more like 20%. The loop is really that repetitive kind of instruction. Sometimes you have to go like 1 million times. You know, each iteration can be very fast, maybe taking less than a microsecond, but when you have millions of these iterations, then it adds up to the execution time. This is generally taken care by the compiler. So, but we might have to coerce or prod a little bit the compiler to recognize those loops, usually meaning applying some compiler switches. But it's generally considered as low effort. Unfortunately, the return tends to be quite small as well. So maybe 20% or 30% are the things that we have observed in the past with our consultancies. Next comes shared memory parallelism, and that's great. It's also focusing on these loops, but this time we're going to have different workers, different cores. You know, a worker is going to have a core of the CPU assigned, and sometimes you can get a factor, 5, or in the very rare cases, maybe 10. So that's better. That's already something that is encouraging. And it's not too much effort, so we had some reasonable successes in past consultancies with that as well. But it's what we consider a medium return. The biggest return, one of the biggest return apart from GPUs, let's say, is to use distributed computing, because at that point you can really spread your computation across the whole machine over multiple nodes. So you're able to scale up massively. And the analogy here would be an assembly line. You have workers, and you now if you have several assembly lines, you can imagine producing many more cars than you would if you just had one assembly line, which would be the equivalent of a serial code. But you need to ask yourself, what can I execute in parallel? Maybe and you want to make sure that the workers are spending a maximum of time on the assembly line and not having too many smokers and or breaks or tea breaks or whatever, not spending too much in communication either. So avoiding interruptions, spreading the amount of work is also something that is important. We don't want some workers to take over all the work and crumbling underneath a certain amount of work, and whereas others are just twiddling their thumbs. Same thing is true for software development and when it comes to distributing tasks in parallel. Now, in this particular case, and that's where the scientist comes in, because the scientist knows the intricacies of the simulation and so forth. And we, the scientist was able to come to us and propose essentially a task distribution scheme such that you have the workers on the horizontal axis, and you have the time steps and so forth, but each worker essentially completes the same amount of work. If you're careful, you can arrange or assemble the work in that particular way or pattern. I'm not going to go too much into the details, but it's a fairly sort of semi-unstructured way of assigning the work. The other thing that is important is that after every time step, so every row essentially, there's a certain communication of data that needs to be performed, and you can see that, for instance, cohort, the boxes are colored according to cohorts. Number 4, is going to take some data from cohorts 0, 1, 2, and this is communication, so that takes time. And the communication takes place across nodes, across cores, and can impact the performance of the parallel code. So what we did, we actually didn't do the implementation. What we did was we wrote an emulator. Given the characteristic of the particular code, we decided, well, let's, before we put our fingers into the code and we make all the changes, let's just see how much parallel performance we would be able to achieve. And so on the left-hand side, you have the parallel efficiency, or in the best case would be 100 or 1, 100% or 1. And you can see that, as depending on the cases, when the number of workers increases, then you get it comes down, but it's still a pretty good parallel efficiency that in the end would translate into something like a 90 times faster code, which would of course make a huge difference. On the top right, you see the extract sort of information from the profiler, which is a tool that we use to identify what's going on in the code. I tend to look at it as some sort of an X-ray machine, for the body, but instead of being applied to a human body, it's looking into the code and trying and helping us understanding what is going on. So. I have reached now the summary, and we. Sorry. And the main thing here is that there are many ways to skin a cat, and there are many ways to accelerate the code, and essentially what we do is we work with the scientist to figure out, which approach is actually the most beneficial in their case. And this is super important because the scientist essentially is going to continue develop the code or continue with the research. We're going to step out, so the scientist will have to become familiar and supportive of whatever approach is taken. In this particular case, I think we found that MPI parallelization, so distributed computing, is likely to provide the best bang for the buck. But there are other ways. GPUs, we had some consultancies where we achieved really, really good speed up with by offloading the computations on the GPU. That's something that we didn't look into in this particular project, but it's definitely something that is worth looking into. There's another way of performing parallelism, which is called workflow parallelism, and I think it's a little bit similar to what Daniel is invoked in terms of flow and pipelines and so forth. Sometimes you can, inside these pipelines, you can execute actually a lot of tasks in parallel, so you can exploit that. Finally, I just wanted to point out that Murray, who's here, and Maxime gave a talk that I think it was the first day on Wednesday, but maybe it's recorded. So that's a talk that goes through the task parallelism that you can achieve in Python. So it's complementary to what is presented here. I should also add that that you can use multiple approaches sometimes, so you don't have to limit yourself to just one. So this was part of our consultancy service at NESI. We love to work with scientists. We love your science, and we think that we are at the service of science, right? And so if you have anything you want to collaborate, you want to reach out to us, we have George here who can answer your questions if you have any, and we're always happy to talk to you. Thank you.
Thanks, Alex. It was great. Does anyone have any questions? We've got about 5 minutes to go before the break, so a little bit of time made up.
Thanks, Alex. I'm interested in that particular case today that you mentioned and what you see of the future of that. You have the scenario where you help someone, you intervene at a point in time, you optimize things, and you give it back to the researcher, and also that you highlighted that in this case, it's someone that's from a different country, and so what would you like to see happen, and what do you think will happen with that particular project, and how your interventions might continue to be of use and value to that scientist over time?
So in that particular case, I think we're in discussion. I will meet the Ina next week or so. I think she's visiting New Zealand, and more discussions are on the way to have another sort of phase 2 of the project where we would actually do the implementation. In general, I think where I see a lot of benefits is in that sort of collaboration, and I think we heard it from Tricia, is you know, we have the researchers and the experts in some fields, and then we have research software engineering on the other hand, which a lot of students may not be, you know, didn't get any course or were not really educated in, and so there's this fantastic sort of crossing between these two fields, I think, which you know, can bring a lot, and all these efforts, which have also the benefit of breaking the silos between the different departments and so forth. The NESI is sort of at this cutting, sort of on this cutting plane and cutting across all these different efforts. So, you know, fisheries, but we recently worked with people who work solving the Einstein's equations, and we're currently working with somebody doing kinetic Monte Carlo. So it's extremely stimulating. So it's something that these kinds of effort, whether as part of NESI or within your own university, I think are extremely valuable. University of Otago actually right now has RTIS, which is fulfilling that role as well. So I see that you are sitting next to Murray, so you can have a good conversation about the benefits of these approaches.
Fabulous. Any other questions from anyone? Great.
Thank you.